Okay, I'm going to run through yesterday's lesson again. I'm not going to rewrite it, but I will try and point to things as we go through, and hopefully I can get the same key points in. Okay, back in P2, you've come across a way of expanding brackets without having to individually do each expansion for A times B, A times A times A times B, B times A, B times B, and then do it again for another bracket, and then do it for another bracket. You came to the binomial expansion, which uses the combination formula, which is this n over 1, which will also be written as nr. If you're actually in Cyrillic countries, or your tutor, you've got a tutor in Russia, what they would write is probably C, R, N. They'll do it that way round. You shouldn't get confused, because the n value must always be the maximum out of these two. R can only ever go up to it. Okay, so just a little thought for you if you're using a local tutor. The problem you've got is this only works for an integer, positive integer n. And that's because this n keeps getting raised to the power of a factorial, or being factorialized, which is multiply a number by every single digit down to 1. And you multiply them all together to give this number. Now, this is attributed to Newton, that he made the following realization. He realized that if you consider n factorial, that's actually the same as n times n minus 1 factorial. And what he's trying to say, he thought, was basically that if you know 5 factorial, if you don't know 5 factorial, but you know what 4 factorial is, you just have to multiply it by 5. If you want to know 5 factorial, but you don't know what 4 factorial is, you can do 5 times 4 and then times 3 factorial. So he was able to expand these out by using these additional terms. And when you rewrite this expansion formula using the factorials, you get the stuff in purple. The reason this is rearranged into 1 plus x is there's some nice features that come about from the final form of this, if you have it in this form. There is a form which uses a and b, but effectively you always convert it into 1 plus x to do the expansion. So what he discovered when he wrote them all out was, if he started replacing the n factorial with these expressions, what he found was, on the numerator he could cancel the n minus 1 factorial with the n minus 1 factorial denominator. Do the same on the next one. Next one over is an n minus 2 factorial, so we couldn't deal with the n or the n minus 1, but the n minus 2 factorial, they will cancel. And if you keep going, it continues forever that way. So the simplified form of it, 1 to the power of n is always 1, and that's part of the reason why this form is used, is that these numbers, these expressions stay reasonably simple. The 1s wind up either returning to 1, or they're part of the overall pattern. And if you simplify this expression, the factorials have disappeared. The 1 factorial is 1, so we've actually got n times 1 times x, so nx. Next one, we've got n minus 1. That's over 2 factorial. And then the 1 and the x. A little tip for you is, yes, this is the way the formula is presented. When I'm doing actual work, I tend to put the factorial part with the x term. I'll tell you why in a moment. It's all to do with what n can be. Do the same things with the next terms. Cancel the n minus 1, n minus 2, cancels through. The 1 goes to being 1. Doesn't matter what this is, as long as it never turns around to being... actually, no, it always goes to 1. Doesn't matter what this is. X cubed over 3 factorial. And this part here is a general term in this series. Now, a series is a sequence of terms that follow a pattern, but they get summed. So this is the general term for position. Position R plus 1 actually. So this is always one higher. So that's term 1. Term 2 has a 1 factorial. Term 3 has a 2 factorial. Okay, so this is actually the position R plus 1. Right, the advantage to this now is because the n's no longer have a factorial on them, they're not limited to being integers. The n can now be a negative number or a fraction. Has a problem that now, whenever we do this expansion, because none of these terms can ever become 0, so n minus 1, we never get to a point where these are going to be 0. This continues forever. So it can wind up working around, and it continues forever to give us, so we can only ever use it for approximations. There is a second problem, that it's only actually useful if you were to consider in the approximations, if these numbers start off with 1 and then we get another value on it, they only actually become useful if the values, the changes for each part get smaller and smaller and smaller, so that we actually get, when we add them all up, we get to some sort of limit value. And the only way this can happen is if each of these x terms are getting smaller. It doesn't matter if they're positive or negative. So this x term must be bigger than the x squared, must be bigger than x cubed, must be bigger than x to the 4, must be bigger than x to the 5. The only way that ever happens is for numbers less than 1. So we get the limitation on this, that the size of our x value must be less than 1. But now n can be any real number. That's a fraction, it's any form of decimal, it can include integers, but if this was an integer, it's better to go back up to this one. Actually, it doesn't matter. If you use an integer in here, one of these terms start becoming 0 and it drops out anyway. So you can use this for integers if you can get it into this form. Okay. So, a couple of examples for you. We want to expand, and they often will tell you up to x cubed, sometimes x to the 4. That's quite high accuracy for the sorts of numbers we're dealing with here. And what happens is, that's a mess. Sorry. So what happens with this is we need to identify all our parts. Now the first part with this example is to replace the square root, we're doing a power of a half. So my n value is a half. The x part of this is the whole expression after the whole one. So this x is going to be replaced with minus 2x. And I will always put it into a bracket. Okay? So when I start putting these numbers in, I put in the 1, I put in the n, which is the half, and I put in my x expression, the minus 2x. I add on the next term. The next term is n minus 1, which is minus 2, and the minus 2x squared. So the whole of this has to be squared to create 4x squared. Okay? And this is where I said the factors I normally put on the x side. I put them over here because it helps a lot of the time when you get fractions here. Keeping the factorial over on separate is nicer, and it helps us solve the problem. Helps us keep things organised a little bit better. So this is why, for me, you'll always see the factorial written under the x squared, x cubed term, if I can. If not, I'll put it on just before it as another fraction. So what happens when we go through is we now look for what can cancel. And what can cancel in this one is the 2 cancels with the 2. So we now get a negative x. This one, we've got a 2 squared on top to give us 4 squared. Well, those 2 cancel with that 4. And the x squared is over 2 factorial. We've got a positive here, but a negative because of that negative there. So it's a negative x squared over the 2 factorial, which is 2. Go to the next one where we've actually done another subtraction. And we've got, where's my pen gone? There's my pen. So this is now a negative 8x cubed. Look at what we can cancel. Well, 8 can cancel with those 3 denominators there. The 3 of the 3 times 2. So that 3 cancels with the 3 here. And when you look at our signs, we've got a negative times a negative times a negative, so it's a negative term. We've got 2, 2, 2, the 2's all cancelled here, so we're left with just that 2 as a denominator. So we've got x cubed over 2. And this would continue in the same way. We should also say what values is this valid for. So it's only valid if what was x is smaller than 1. Okay, just get my pen back, sorry. Bigger size. So the minus 2x has got to be smaller than 1, and that's why it's inside a modulus. The modulus deals with the minus, get rid of it. So the modulus of x becomes smaller than a half. And that tells us that we've got valid approximations. If x is bigger than this, the numbers blow up and they get further and further away from the number you calculate. Okay, so it is only a valid approximation if x is less than a half. Now the second part of this question is about approximations. And the approximation stuff, what I suggest you do with it is don't get bogged down too much with what they're asking you to prove first or find an estimate for. If they've given you a suggested value, put that suggested value in. So we put in the value, put it into both sides. We put it into the original expression, 1 minus 2 times 0.1 gives us 0.98. This is a square root of 0.98, sorry. And this is approximately equal to 1 minus 0.01 minus 0.0001 over 2 minus 0.0001 over 2 for each term. Do the calculation. This will convert. This is getting smaller. Notice each of these are getting smaller than each other. So each term gets smaller. This is why it converges, and our convergence means we get a final number that's a reasonable estimate. So this is an approximation. The question actually said, find the square root of 2. Now, the original versions of these questions, which might still be around, say, hence by choosing a suitable value. I might look at those a bit later. When we get to the end of the chapter, we'll come back to the other form because they imply this is the only form they're going to use. They've given us a suggested value. So we now look at this 0.98. And how can I manipulate that 0.98 to turn it into a 0.2, a root 2? Well, if I multiply it by 100, so I've got 0.98 over 100, that gives me 98 over 100. The 98 over 100 can be split out into 49 over 100 times 2. That's where my square root of 2 comes from. And the 49 and the 100 can both be separated out to give me 7 over 10. So I do the square root of these two parts. 7/10 times the square root of 2 is approximately the value calculated before. If you rearrange, you get square root of 2 is approximately 10 over 2 times 0.89999495. and when you calculate it, it comes out as a reasonable approximation for the square root of 2. The reason that this is often used, or this is taught and heavily used, is until about 20 years ago, the algorithms for calculating these roots were fairly secret. Companies like Casio and Texas and HP made a lot of money by being able to calculate these roots in a small calculator device, the pocket calculator. And it's only 30 years ago that they started being able to do arbitrary ones. And it's finding these expressions, like this example 3, finding the suitable expression, a suitable value to use an approximation for the particular question that you would like to do, and then being able to do the expansion. So there was a lot of money for the mathematicians that came up with good algorithms for them. Final example is this example 2b. We've got the approximate expression for x cubed, so we need to expand it. We go through the same process. We identify n is minus 2 for the power. That's what puts it, the minus puts it on the bottom. The minus is what stops us using the normal formula. We've got 1 plus, and then everything that's being added, everything after the 1 is what replaces my x, so the plus 4x. We expand it, so we use the formula from the book. It's in the P2 part of the formula booklet. We use the formula and lay out so that we put in, start with 1 plus our power, minus 2, times our x value, the 4x. The next value, we do our minus 2 again, times minus 2 minus 1, which is minus 3, times my x value squared, so 4x all squared, gives me 16x squared over 2 factorial. The 2's cancel, but the signs don't, so we've got a positive, a minus times a minus is positive, so it's a positive. We've got 3 times 4 squared, which is 16, so 48x squared. Moving on to the next one, we've got our n, minus 2, minus 3 times minus 4. We've got 3 negative signs, so that's negative. We've got 4x all cubed. 4x times 4 is 256. People who use computers should recognise that one. The 3 and the 2 from the 3 factorial cancel with the 3 and the 2 from the n and n minus 1. So we now have this expansion. State what values it's also approximate for, so we can say that if x is less than, plus 4x must be less than 1, so 1x, or the size of x must be less than 1 over 4. And then if you put numbers in, you can find approximations for a number of different things that are going on. I don't think I was going anywhere with this one. So that's the summary from yesterday's lesson, hopefully on a clearer microphone.